Hi everyone. Sections 5.4 and 5.5 will cover a bunch more trig identities. I'm going to require you to know or figure out 19 and be able to use 8 more. So 19 plus 8, 27 total. So I have a separate handout. You can get it off my website also, and we're going to go over it. But here's the overall schematic. I'm going to start with the 3 sum-identities. I'm not going to prove these 2 on top, but I'm going to start with the overall sum-identities, numbers 1 through 3. Although sometimes the difference identities are proven first in books. Now we're going to go through how you can get from these lowly sum-identities, you can get all these other identities. In fact, one of my best math students of all time told me that she didn't have a very good memory, but she was able to memorize the 3 sum-identities and she was able to figure out all the others. This is a great exercise during a commercial break, or maybe during the news. Start with the 3 sum-identities and derive the other 16. These 8 over here, again, be prepared to use them when you see them. All right. Let's start by introducing the 3 sum-identities. And in principle, you use algebra and basic trig identities to go from there. All right, things that you need to memorize. At the very least, you have to memorize the 3 sum-identities, and then you can go from there. So, the sine of u plus v. What is the sum-identity for the sine function? It is not, don't engage in wishful thinking, it is not sine of u plus sine of v. It does not break up like that. Square roots don't work like that. Logs don't work like that. Sine and cosine don't work like that either. You do not break things up like that. Instead, and again, this comes from proofs, which we won't go over, but this comes from the sum of the mixed up products. Well, that's a way to think about the right-hand side. The sum of the mixed up products. Again, parentheses might help. The sine of u plus v is sine of u, cosine of v, plus cosine of u, sine of v, is the sum of the mixed up products. It's a real tossed salad here, right? So it's all mixed up. Now, by the way, if your u and your v tend to look alike, then maybe when you're applying the identities, you might prefer a and b, or maybe x and y, assuming these 2 don't look too much alike. But if your u and your v look too much alike, then maybe you might prefer one of these other pairs, and then sub back if necessary. Actually, one reason why I chose u and v is that often we substitute into u and v, like when we're dealing with known angles, like 30 degrees. Anyway, think of sine of u plus v not like this up here, but as the sum of the mixed up products. Cosine of u plus v, I'll put it in blue. Cosine of u plus v, again, not cosine of u plus cosine of v. The sum identity here, think cosine product minus the sine product. Cosine of u times cosine of v, the product of these cosine values, minus sine of u, sine of v, minus the product of these sine values. If you remember the cosines minus the sines, you should probably remember this. Or maybe the cosine product minus the sine product. Tangent of u plus v. In green. Tangent of u plus v. Now, this is hard to memorize. I think of it as the sum over 1 minus the product. By the sum, I mean tangent of u plus tangent of v over 1 minus the product. Tangent of u times tangent of v. So these are our 3 sum identities that you should memorize, maybe with these mnemonic devices. And from these, we can get all the others. Be prepared to apply these identities both left to right, like you're expanding, and also right to left, like you're condensing. And we're going to apply these identities in both directions. So now let's go from the sum identities to the difference identities. And these will be numbers 4 through 6. Now, in terms of memorization, it's very straightforward. Here are the sum identities. Here are the difference identities. Look familiar? Basically, you take the sum identities, and there's a trick. You change every sign in sight. You flip every visible sign. You flip every visible sign. So every sign in sight. The plus signs here go to minus signs because we're doing difference identities now. Right? The plus sign from before becomes a minus sign now. The minus before, remember that the sum identity for cosine had a minus in here. And that's important because that helps explain why the derivative of cosine of x is negative, or the opposite of sine of x. It's that minus sign there. Some of you who have taken calculus know that fact. The derivative of cosine of x is the opposite of, or negative sine of x, is because of that minus sign. The minus sign turns to a plus sign here. Likewise, for the sum identity for tangent, the plus and the minus go to a minus and a plus. You flip all the visible signs. I say that you flip every visible sign because there is an implied plus sign in the front, here, here, and here, but you don't flip those to minuses. These don't flip to minuses. So you flip every visible sign, every sign you see, plus or minus, even on the left-hand side. And why does this trick work? It almost seems like magic. It's magically convenient. Why does this trick work? So I can actually prove or derive these from the sum identities. So for example, okay, why does the sine of u minus v equal this? All right, well, the sum identity for sine is in red up here. Sine of u plus v is the sum of the mixed up products with the plus sign in the middle. Now, to analyze sine of u minus v, here's the idea. We're taking sine of u plus v, and we're placing v with its opposite. We're substituting v with its opposite. And of course, u plus the opposite of v is just u minus v. So these are equivalent. We're going to apply the sum identity where we're taking the sign of the sum of u and the opposite of v. So every time we had a v up here, we're going to replace with the opposite of v. Now, is cosine even or odd? Is cosine even or odd? Cosine is even. So it's these guys again. Cosine is even. Which means, what happens to this negative sign or opposite sign in here? It dies. We can delete it. It drops out. Cosine of opposite of v is just cosine of v. But what about sine, S-I-N-E? Sine is what kind of function? Even or odd? Sine is odd. So what happens to this negative or opposite sign? It pops out. So over here, this sign dies out because cosine is even, but this guy pops out because the sine function, S-I-N-E, is odd. So the plus sign turns to a minus sign. It comes down to the even and odd properties. Cosine is even, while sine and also tangent are odd. Look at cosine. Here's the sum identity for cosine. If you replace v with its opposite, again, cosine doesn't care. That sign dies out. But sine cares. That negative sign would pop out. Make that a plus. Over here, tangent of u plus v. Tangent is odd. If you replace v with the opposite, tangent cares. This negative sign pops out. Tangent cares. We have negative v here. The negative sign pops out, makes that a plus. We're not changing the u here, or tangent of u. But when the v's go to their opposites, then tangent of v will go to their opposites. So we flip these signs. So the reason why we flip all the visible signs to get from the sum identities to the difference identities is because of the even-odd properties. Cosine is even, while sine and tangent are odd. So we now have 6. Memorize these 3, the sum identities, then you can quickly get these additional 3, the difference identities. We're up to 6. Also, we're going to see in the next video how the sum identities will lead to the double angle identities. And that'll give us not 3 more, but eventually 5 more. Next time.